Good day, stat students. And today we're going to talk about section 3.2, the association between two quantitative variables. And so in 3.1, we took a look at the relationship between two categorical variables. And you saw how we did that analysis with the tables and everything. Well, I'm going to show you what we should be looking at to see if we have an association between two quantitative variables. All right, so we still have a response variable. And what we're going to find out is that the response variable is going to get a y in this type of analysis. And so you'll see the reason behind that here in a little bit. The explanatory is going to get the x. And so I always remember this, that the x explanatory is going to get the x. Okay, so explanatory variable x, response variable y. All right, so let's take a look at this example. Is there a significant relationship between a city's latitude and its average area temperature? And average area temperature is going to be measured in Fahrenheit. Now, so this would be a research question. You know, is there a significant relationship between these two variables? That's a good, solid research question. And so now, just in case you've forgotten latitude, let's say this is the Earth. All right, and here is the equator, and sitting at the equator is 0 degrees latitude. Now, I'm not saying that this is temperature, okay, when I say degrees. Remember how you can have degrees on a circle? Well, you can have degrees on a sphere, all right? And so at 0 degrees latitude, you would have to be at the equator. At 90 degrees you would be at the North Pole, and at minus 90, you would be at the South Pole. Okay? So, let's think about this. If you're in North America, all right, and you are, say, in Florida, and it's January, you would say it's probably going to be, you know, reasonably warm. And then as you move north, okay, as you move north on the globe, all right, what's going to happen to average area temperature is going to go down. And so that's why I'm saying here, is there a significant relationship between these two variables? All right. So as one changes, does the other one change along with it? Okay. So my final thoughts on latitude is that just remember it's a measurement of north to south. Okay. All right. Let's move on. So define which is the response variable, which is the explanatory. So let's see here. Latitude, a city's latitude, I think is doing what? The explaining. That explains why the average area temperature is what it is, and so average area temperature is going to be the response variable. And so average area temperature is going to get the y. Okay? So I have some data here. And I just went ahead and picked out 10 cities in North America. We have Miami and Mobile, Alabama, Baltimore, Maryland, Cleveland, Duluth, Minnesota, okay, and places in between, okay? And so here's its latitude, and here's its average area temperature, all right? And so notice as latitude appears to be going up, what's happening to average area temperature? It appears to be going down, okay? So what we can do is we can take this data and take a look at it graphically, all right? And so scatter plot is a plot comparing two quantitative variables, all right? And so this is the reason why we give the variables x's and y's. So remember, this is the x-axis, this is the y-axis, okay? And so latitude is the x explanatory, and average area temperature, that's the y. Okay, so we start with the first city. We got Miami, and we got latitude 26. Let's see, latitude 26. That's about right. I don't know, about here. And then we have average area temperature 67, way up here. So maybe a dot is going to show up about right there. Yep. Okay. And then you would just go to the next city. We got Mobile, Alabama. We got 31. So 31's right there, and average area temperature is 50. And so, I don't know, maybe somewhere around here or so. Okay? I missed a little bit. Right there. Okay? And so, you go to Lincoln. All right, there's Lincoln. Nebraska. And then we can fill in the rest of them. I think you get the point. Okay. Now, I think you're going to see that there's 9 dots here. Okay. And the reason why you maybe only see 9 dots, is that let's see, Lincoln, Nebraska, and Cleveland are both at 41 and 25. Okay. So there's actually 2 dots sitting right here. Okay. So they just happen to be on top of one another. All right, so do you see a trend going on here? So it looks like the trend is looking like that. So we got this trend line, it's heading down. And so what we call this is a negative relationship. And so what's happening with the negative relationship? As x increases, y tends to decrease. So here's x, latitude. As x increases, so as you move north in North America, as you move north, what tends to happen? The temperature in January tends to get what? Colder. And so as latitude increases, average area temperature tends to decrease. Okay? And so the reason why we call this a negative relationship is that the slope of this line is negative. Okay? So please don't cringe over that, all right, that we talked about slope. But we're going to analyze slope a little bit closer in section 3.3, okay? But please note that we have a negative slope here, and that means we have a negative relationship. All right, so we're going to use this data, all right? So keep this data in mind, all right? And we're going to see this again in 3.3. For right now, let's kind of shelve it, and we'll come back to it another time. Let's move on to, say, a positive relationship. Here we have height and weight. So generally speaking, as people get taller, they weigh more, okay? But there are individuals that sort of buck that trend, okay? And so all we can say then is as x increases, y tends to also increase with a positive relationship. So as height increases, what happens to weight? It tends to go up too, okay? And the slope of this trend line is what? It's positive, okay? Since we have a positive slope, we have we're going to call this a positive relationship. As x increases, so does y. Well, now those two relationships there are both what we call linear relationships. What's the main root word in linear? Line. So these relationships can be shown with a line. Well, we can run into other types of relationships. So we can run into, this hot mess. We have weight, and we have what? How much they're on the internet, okay? And so do you think there's any kind of relationship between weight and how much they're on the internet? No, okay? And so that's what's happening here. We got this big mess of this big blob of nothing, okay? There's no trend going this way. I don't see the trend going that way for most of the data, okay? Don't be influenced by these 4 dots right here, okay? You got to look at most of where the dots are, and where the dots telling us we don't have a trend. And so what happened to the trend line? The trend line went straight across like that. And do you remember what the value of the slope is when you have a line that goes straight across like that? So if it's perfectly straight across, the slope is going to be 0. Okay, so you should associate no relationship. Okay, you should associate no relationship to a slope of 0. Okay, no relationship, slope is 0. Well, we can run into other types of relationships. We can run into this. And so clearly, this isn't linear anymore, but certainly there's a relationship. Looks like more of a parabola, okay? And so here, we can handle these types of relationships in statistics. But the good news for you guys is that you don't have to deal with it, okay? We're only going to deal with the linear stuff. But we do have to at least acknowledge that this exists, all right? Because we're going to see that again in 3.3, that relationship, okay? But do we have to do anything special with it? No, we just have to acknowledge that it exists, okay? And you'll see what I mean when we get to 3.3, okay? All right, so let's move on to a different concept here. So take a look at this scatter plot. Take a look at that scatter plot. So with this scatter plot, we have dots that are very close to the line, right? Very close to the line. And notice these dots here. What's happening with these dots? These dots are getting, well, they're a little bit more spread out, aren't they? Now, both of these have a positive slope, okay? But clearly, there's a difference in the relationships. Which one would you say is a stronger, which relationship? The one on the left or the one on the right? Which one has a stronger linear relationship? What does your intuition say with regards? Did you say this one over here? Well, if you did, correct. All right. So the closer the dots are to the trend line, okay, the stronger the linear relationship. And as they are spread out a little bit more, the lesser, is the relationship between them. Okay, I shouldn't say maybe lesser. The weaker the relationship is. All right. So this one's the one on the left, strong. This one's a lot weaker than this one. Okay. And so here's the thing: is that slope cannot indicate whether a relationship between two quantitative variables is strong or weak. We can take a look at a scatter plot and say, yeah, there seems to be a relationship. All right. But if I just told you, well, the slope between two, for two different relationships, that by itself is not going to tell you it's strong or weak. All right. And so there's got to be some sort of measurement that tells us how strong or how weak the relationship is. And that's really our next topic, and that's the correlation coefficient. So the correlation coefficient is a measurement for the entire data set, indicating how strong of a linear relationship exists between the two quantitative variables. So correlation coefficient tells us how strong, right, how strong the relationship is. Okay? So let's get into the correlation coefficient. First of all, the symbol for the correlation coefficient is R. I'm not sure where that came from in the first place, but that's what we use. Correlation coefficient, R. Second thing is, here's the range of values that R can take on. It can take on values from what? A -1 to what? A +1, and everything in between. That's all that's saying. So R is something anywhere from a -1 to a +1 and anything in between. The sign of R indicates the type of relationship, and what I mean by that is that if R is a -1, that indicates a negative relationship. If R is positive, if R is, let me make sure I said that right. So if you get a negative R, that indicates a negative relationship. A positive R indicates a positive relationship. Okay? Only makes sense. So what about the numbers, though? What exactly are the numbers telling us? All right, well, let's get into that. So an R that's close to a -1, say that it's less than or equal to a -0.75. So let's say that you get a negative point, say 9. Okay, if you get a negative 0.9, you should say, oh, okay, I have a negative relationship and it's very strong. By the way, let's get this out of the way. A negative relationship doesn't mean a bad relationship. It just means as one goes up, the other one's going down. Okay, that's all the negative means. Okay, don't put a negative stigma to it. All right, it doesn't mean anything bad here. Okay, it just means that we have a negative relationship. Okay, and that the slope of the trend line is negative. That's all it means. All right, and so so if you get a negative 0.9 for R, you got a strong negative relationship because it's very close to a -1. How about if we go to the opposite side of the spectrum? If you get an R greater than or equal to, say, 0.75, say you get, 0.8, 0.85. That's telling us that we have a fairly strong positive relationship. It's pretty close to 1, okay? It's pretty strong. Something close to 0, you're basically saying no relationship. Now, you will probably not get in real data an R that is exactly 0. All right, but you will probably get something like, say, 0.001 or negative 0.002, something like that. You can pretty much say that you have no relationship there. Okay, so close to zero, hardly any relationship. Okay, or at least very weak. So we should be able to interpret everything else in between. So if you get an R, let's say negative 0.75, so between a negative 0.75 and a negative 0.4, so let's say a negative 0.6. Okay, so if you get something like that, what is that telling us? We got a moderately strong negative. Okay, it's not weak, it's not real strong, it's moderately strong. Okay, it's somewhere in between, right? It's okay. But then once you start getting closer and closer to zero, say you get a negative 0.12, that's telling us, okay, we got a negative relationship, and the number's telling us, boy, it's pretty weak. Okay, it's pretty close to zero. You can go on the opposite side. So let's say that you got 0.1 for an R. That's telling us that we have a weak positive. And let's say that you had 0.58. That's telling us that we have a moderately strong positive relationship. Okay. So here's the thing: is that I could show you the calculations for R, but it's beyond the scope of the course. We'll just allow the computer to do it for us. Actually, all it is it's a bunch of z-scores being multiplied together. Okay, and so let's not worry about the calculation itself. So that, can you interpret it? Can you look at a correlation and say, "Ooh, we have a strong, we have a we have a weak, we have a negative, we have a positive relationship"? Okay, that's what we're looking for. All right. Now, one last thing about correlation before we sort of move on to looking at very specific graphs. Okay, is that the slope and the correlation coefficient will have the same sign. Always. It will always have the same sign. So if you have a negative relationship, slope's going to be negative, correlation is going to be negative. If you have a positive relationship, positive slope, positive correlation. All right. And so, but they will not have the same value. It would be a very rare situation that they would have the same exact value. Okay. So don't expect correlation and slope to have the same value, but they will have the same sign. Okay, let's take a look at this. Here, this graph is showing all the dots exactly on the line. Okay, and we have a negative relationship. Okay, negative slope. So that means we need a negative value for the correlation. And since all the dots are exactly on the line, this would be an R of a negative 1. This is a perfect negative relationship. So that's the most extreme from the one side. Let's go to the other extreme. How about a positive 1? This would be a positive, perfect positive relationship. So all the dots are on the line. There's no deviation off of it whatsoever. And to be honest with you, in both of those situations, you can use algebra because we have no deviation off the line. All right. Honestly, there's no reason to use statistics. Actually, statistics doesn't do well when you have no variation. We need variation in our data, okay, to do a bunch of stuff, okay. And so this is really meant for algebra. Okay, how about if you had our big ball of nothing? Here's our big ball of nothing. Okay, really no trend. Okay, trend line's going roughly straight across. And what is that going to give us for a correlation? Roughly 0. All right, so no relationship. And here we have GPA versus height. So do you think a person's height has anything to do with their GPA and vice versa? No, I don't think so. Okay, and there it shows it. All right, so let's take a look at a couple of scatter plots and see what we can come up with regards to the correlation coefficient. So here, it looks like maybe our trend line would go something like that. And so certainly we have a positive slope here. We have a positive relationship. So the correlation is going to be positive. And to me, there's not much deviation off the line. Yeah, we get a couple of dots out here. But for the most part, most of the dots are pretty close to the line. And so I would expect the correlation to be high, a positive positive value that's kind of close to 1. Let's check it out. All right, it turns out to be 0.89. Okay, certainly that's telling us that we have a strong positive relationship between these two variables. Okay, let's take a look at the next one. Here's the next one. Looks like we have this negative relationship here, doesn't it? So we have, oh, that was a horrible looking line, but that's okay. There's our trend line. All right, it was supposed to be straight, but that's okay. Clearly it's negative, and what's going on here is that, boy, it looks like these dots are pretty spread out. Notice you got a dot way out here, and you got a dot way out here, okay? Well, this is getting awfully spread out, okay? So we have a negative relationship, but what? It's not very strong, is it? So I expect this to show up to be weak. And there you go. We have a correlation of a negative 0.29. Okay? Let's check out the next one. Oh, okay. So we have a positive relationship here, clearly. And let's say that there's our trend line. I'm not exactly sure where it would be, but there you go. It was probably a reasonable guess at it. And let's see. So our correlation should be positive. And what do you think about that one? Is that weak or is that strong? Hopefully you say it's strong, and so we should be what? Close to a positive 1. Probably like 0.9899, somewhere around there. Hardly any deviation off the line whatsoever. There you go. That's producing a correlation of 0.99. How about this one? So let's take a look at this one. So maybe there's our trend line. All right, so certainly not as strong as the 0.99 one, but I don't think it's as weak as, say, that other negative one. Because remember we had that dot way down here and dot way up here and stuff, and so to me, this looks like a moderately strong negative relationship. All right, so let's take a look here, and there you go. It turned out to be a negative 0.66. So it's telling us, okay, we have a relationship. It's not real weak, but it's not real strong either. It's somewhere in between. Okay, and I think that we can sort of see it from the the scatter plot. Sorry about that. The scatter plot. We can see it from the scatter plot, and we can also see it from the correlation coefficient. Okay. So let's take a look here. I got here, what's the value of the correlation coefficient? So this is the type of question that you should expect here. Because we're not going to calculate it, but we should be able to interpret the correlation coefficient. We should be able to look at a scatter plot and understand what kind of correlation we should be getting. Correlation is used in a lot of different disciplines. In business, the stock market uses the correlation coefficient. Certainly, like psychology, they look at the correlation coefficient. Engineers, so on and so forth. Medical field. So a lot of different disciplines use the correlation coefficient, and so we should have a pretty good idea. Well, we can always allow the computer to do the calculations for us, but we should have a reasonable way of looking at a scatter plot and saying, based upon these 4 answers, I think this should be our answer for the correlation. So let's take a look here. So if I ran into the question like this on the test or for homework, I would do a process of elimination first. So first thing I would eliminate is this guy right here, D. Why? Because that's not a valid correlation coefficient. That's out. We know that one. 2, since this is negative, okay, this is clearly a negative relationship, okay, I can eliminate what? B. That's showing a positive relationship. So I'm down to a negative 0.05 and a negative 0.88. So we should say to ourselves, what would a negative 0.05 look like? Well, that's pretty close to 0, so that's saying a pretty weak relationship, right? And so a negative 0.05, I think you would have dots that are pretty spread out, more like this, okay? And so I don't think we have that here, okay? So, yeah, I think we can do what? eliminate that guy. All right, and so this looks like a moderately strong to a very strong, relationship, and it looks like our best answer is C, and so it looks like this looks like a strong negative relationship, and there's the actual correlation coefficient, negative 0.881. Okay. All right. Some last things about correlation. One, it does not depend on the variable's units. All right. And so it doesn't matter if we went ahead and measured one variable in inches, all right, and then changed it over to feet, all right. It doesn't matter if the other variables measurement doesn't change, okay. If we went from inches to feet, or vice versa, or just change one and didn't change the other, it's never, ever, ever going to change the correlation coefficient. All right. 2. So the example I gave here is that going from, say, pounds to kilograms, it just doesn't matter. Okay. The units all get canceled out. Units don't matter here. Okay. It does not matter which variable is x and which variable is y. All right. Does with slope, but not with the correlation coefficient. Okay. And actually, slope, the variable, the units of the variable does matter. Okay, that's why the book is bringing this up. It's saying, okay, correlation and slope, they have some similar characteristics, but here are the different characteristics. Here's the difference between them two. Okay, and so it doesn't matter which variable is x and which variable is y. You can switch them out. It doesn't matter. The correlation coefficient isn't going to change. And then correlation is not resistant to outliers in any way, shape, or form. Okay, and so let's say that, for an example, let's say that we had this type of relationship, and this is suggesting a very strong positive relationship between these two variables. Okay, and notice the correlation here turned out to be 0.99. Okay, and what I did, I went to the computer and I said, let's add an observation to this. This is what I did, is that I added this guy down here. Okay, and so that's an outlier, clearly. Okay, it completely bucks the trend. The trend is going like this for these 10 observations, and we had this one crazy outlier out there. Okay, and so notice what happened to our correlation. It went from 0.99 down to 0.5, just like that, just by one observation. All right, and so the correlation coefficient is not resistant to outliers. All right. And so you got to sort of pay attention if you have outliers in your data or not here. Okay. All right. So what we're going to do is we're going to, in the next section, which I believe is 3.3, we're going to take a look closer at the equation of that trend line that I kept on drawing for us. All right. All right. So have a good day. That is the end of this section.